post. Hopefully, I'll have no problems converting this to a YouTube video. Sometimes it doesn't want to cooperate, but hopefully I'll be able to do this easily. And I'll let you know how it is, where it is, so that you could listen to it should you want to. I'll get that on the website at the appropriate time. So what I want to do today, I do have a PowerPoint, which I'll go over with you, which gets into the nitty-gritty of modern test theory, because things are going to get a little more complicated than they have been up until now. I think from what I'm seeing in terms of the homework, everybody's doing pretty well. And before we go into the modern test theory stuff, I want to just ask if anybody has any specific questions about any of the homework assignments that have come to pass already. So I'll just turn it over to you and just ask for questions first of all. So I'll spend a few minutes answering any questions you all might have.
I have a question.
Okay.
I was wondering, are you planning on posting the rest of the questions like you did so kindly for us that first time, so we can just review everything and make sure we're on track?
I could do that. I wasn't planning on it. I mean, the first time it was just that because of winter session, I was running a little behind, and I wanted to make sure you all had access to everything. But is there general interest in my posting answers to all the questions, even the ones you didn't do?
I found it helpful, and I don't know if, with the midterm exam, if that would be good review for us.
Yeah, it might be, actually. Anybody else want it?
Sure.
Okay, so I think what I'll do is I'll just, maybe I'll just post it. Let me just make a little note to myself. I'll post it, and what I'll do, because I have to put it together, is what I'll just kind of pull stuff together from past groups. So I'm going to post homework 2 responses. Okay, so I'll put that, you know where I'll put that? I'll put that somewhere under the homework 2, which is last week's part of the Moodle site, so that you can access it from there.
Great, thanks so much.
Okay. Other questions? Either practical ones like that one or content ones? Hi, Brittany. I guess she hasn't heard me yet. Hi, Brittany. How are you?
Hi. Sorry I'm a little late.
It's okay. It's okay. I was just asking whether there were any general questions before I go into my teaching lecture modality. Just want to make sure that people are all doing okay and that you're able to keep up with the reading and that it's making sense. And obviously, from what I can see of the homework, you're all doing okay with that. And so far, we really had what I would describe as more kind of, I don't know, the nitty-gritty of designing tests and how you do that, and some of the issues that you worry about in terms of how do you sample, different ways of sampling, and before that, something about the development of a construct, the questions that ask you to come up with a test to measure a particular psychological construct, and then to research the literature and see how others have derived that construct is really something you would do if you were going to design your own test. So far, what the book has helped you understand, I think, are the different steps in developing a test. So that when you buy a test from a test publisher, somebody, probably not the publisher, but somebody who developed the test in the first place has gone through some of similar steps in developing the test. What we're going to be talking about from here on out are a little more complicated issues having to do with the reliability and validity of the test, and how we would know that the test is both reliable and valid, and some ideas about how we actually measure a construct that get into a little more complicated stats. And so what I want to make sure we do today is I'm going to explain it at a more conceptual level. I'm less interested in having you understand in detail some of the statistical underpinnings than I am in having you understand conceptually what we're talking about. I think it's highly unlikely that any of you will go into the business of becoming test developers, although never know, maybe you will. So given that you'll be more test consumers in all likelihood than test developers, what I'm interested in your understanding is how to pick good tests. And that's why the final assignment is about critiquing an existing test in print and some other different things that we look at when we determined how appropriate a test is for our personal use. And that's a decision that you have to make each and every time you use a test, especially if you're doing a test battery in an agency where every time a client comes in you do 4 or 5 different tests, and that's what you do, obviously the decision's already been made for you. But if you're going to develop a private practice in which you do some psychological assessments, you may go through a process in which you first determine what are the appropriate tests and how adequate are they for your purposes. And when you get to a dissertation, you might want to use psychological instruments, not so much for assessment purposes, but for the purposes of collecting data for your dissertation. And yet some of the same ideas are going to apply there in terms of how appropriate a particular test is for the measurement of a particular construct that you might be exploring for your dissertation. So I just want you to kind of, understand a little more conceptually what this course is all about, because the book gets very, very concrete and very nitty-gritty, and some of the homework assignments are about being able to carry out some of the computations to answer the questions. But understand that the reason you're taking this course is so that you can be a well-informed consumer of tests. There are a lot of them out there in print, literally thousands and thousands of them. Some of them are very good tests. Some of them are really bad. And they're on the market because somebody makes money selling them. And if you buy a bad test, then you basically have enriched somebody who has produced something that's really not worthy of your time and your money. So, buyer beware. Make sure that when you determine that you're going to buy a particular instrument, whether it be for your dissertation or whether it be for your practice, that you're buying something that is a quality thing. And hopefully after this course you should have everything you need to make that determination. So enough of I'll get off the soapbox. I was on my soapbox there for a while. But are there questions about, overall kinds of things like that? And most of you have muted, so if you want me to hear you, please unmute yourself. Skylar, are you trying to say something? Because you keep coming up as trying to say something.
Oh, no, I don't know why that's happening. Let me mute the microphone. Maybe it's too sensitive. Sorry.
Yeah, it gets really sensitive. If you sneeze, your name comes up on my screen here. So if you're not going to talk, just please go ahead and mute yourself so that we don't have to hear you sneezing or anything else like that.
Okay, sorry about that.
You do want to talk, but please remember to unmute yourself when you want to ask a question or talk, because otherwise we won't hear you. So anybody have a question? And again, unmute yourself before you talk, or we won't know that you have a question. Okay, well, then if nobody has a question, let me just move towards doing the PowerPoint. I'm going to show you my screen, but give me a second to get everything set up so that I can show you the right thing on my screen. Hold on just a second. Okay, hopefully, whoops, no, you don't want to see me. I'm not that interesting. All right. You can still see me. I don't want you to see me. Okay. Hopefully now you can see my screen and you don't have to look at me. If you're on the phone, then you probably don't have access to my screen. But if you're on your computer, you should see my screen. So if there's anybody who's on your computer and cannot see my screen, could you let me know? not sure what I could do about it, but I can at least give you some indication on how you can see my screen. So I'm going to assume that you all see my screen. And if you can't see my screen, I've also put the PowerPoint up on the Moodle site. I can't remember now where I've put it. I think it might be in the beginning, the introduction piece. But I'm going to move to the slideshow function here. So as I mentioned before, we're going to be talking about modern test theory. There are two general kinds of approaches to thinking about how we measure traits in individuals. One is what we call classical test theory. It's actually the very next chapter that you'll be reading about and doing homework from, and immediately following that will be the first chapter on modern test theory. And I believe that the next homework assignment encompasses both the classical and the modern test theory. So what are these? Well, first of all, you should think about what we're doing here is we're trying to measure a construct, but every theory about how we measure construct has a model about what is happening. So imagine somebody that builds models for a living, maybe an engineer who builds bridges. First thing that engineer might do is develop some kind of a plaster or wood, or maybe somebody on the line is an engineer and can help us with my metaphor here, but first that person would develop a model for how to build that bridge before setting out to build the bridge. So similarly, in our field, and particularly with the use of statistics, we build a model for what we think is happening. And the model that classical test theory uses is that if you give somebody a score on a test, that score represents the true amount of the construct the person has, let's say intelligence. And of course, something like intelligence isn't directly knowable. We can't see it happening inside the person. Think about the black box, which is the person, and our lack of ability to actually see inside what's happening, but we can measure it. And when we measure that, we're actually measuring how much of that intelligence the person actually has, which really is kind of unknowable, plus some amount of error variance. So X, which is the score of the person, is equal to the true amount of that variable that they have, plus E, some amount of error variance. Hopefully you're all with me. Please, 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 if this gets confusing, stop me, because otherwise I will keep talking. And that's all fine and good, except modern test theory says, well, it's much more complicated than that. You have to consider both the person and some of the attributes of the items on the test. And so this is a different kind of a model about what it is we're measuring, where it's much more, modern test theory, or theorists would say, than simply the true amount of that construct that they have plus error variance. We also have to look at some characteristics of the items. And in the modern test theory chapter, your book is going to present two different approaches or two different models to understand what it is that a score truly represents. So if you got a score on a test, what does that really represent? And the two models that the book will provide to us is what's known as IRT, or item response theory, and second set of models are the Rasch models. Well, people that talk about modern test theory as compared to classical test theory says, well, what's nice about IRT, or item response theory, is that when we measure a construct using that theory, we'll get a better fit. So in other words, when we measure how much intelligence they have, we'll have a much closer assessment of that construct than if we used a more classical model for measuring that construct. And IRT uses up to 3 parameters. We'll come back to this notion of parameter so that you can see exactly what we're talking about. This approach to measuring the construct is very descriptive because what it's trying to do is to fit the model to reality. And actually that's really what happens with people that develop different theories about how to measure a construct. They're trying to get a model that's going to fit that model in the very best way possible to the reality of what we're trying to measure. The Rasch model, which is the other approach that your book in the modern test theory chapter is going to talk about is a much simpler approach, and it looks at a single parameter at a time, and it is prescriptive in nature because it's trying to fit the data to the model, so it's working in reverse order. Regardless of whether we're using one of those two models, unlike classical test theory, in which the scores of the same person may vary from test to test depending on the difficulty of the test. So, for example, let's say you're taking a course on English literature. Imagine yourself back in high school taking a course, and you're studying English literature, and your teacher gives you a final exam. You have Mrs. Jones, she's your teacher, and Miss Smith next door has the other class, also studying English literature, and she has a different test. At the end of the semester, you get your grade, and you talk to your best friend who's in the other class, and you find out more about that test, and you realize had you been in that class, you would have gotten a higher grade. So it's kind of not fair because you're getting a B in the course, and had you been in the other course, you would have gotten an A. That would be an example of tests that that are going to measure the attribute, in this case, understanding of English literature. They're going to measure that attribute differently depending on the nature of the test. So the score that you might get is going to vary from test to test depending on how difficult the test is. And I'm sure you can flash back to times in high school when you had exactly that experience, and it was very, very frustrating. The beauty of modern approaches to test measurement, in IRT in particular, is that when we measure the construct, the score that you get is going to be independent of how difficult the test is. So I think you can see that that would be much more beneficial, because then we'll get a much clearer notion of the construct, or in this case, how much you know about English literature. So one of the articles that I had given you as an extra article is an article by you that tries to explain modern test theory in slightly different language than what's in the textbook, and I am going to try. I'm not sure how well I'm able to do this. I'm going to try. I've got that, a couple of articles from, oh dear, let me think. Where did I put that? A couple of examples from the U article right here on my screen. You should be able to see now. You should be able to see a table. Imagine you're giving a test, and if you look at table number 1, the item has the test has 5 items rather, and as you can see, person number 1, denoted in purple here across the top row of this table, got item number 1 correct. A 1 means they got it correct. A 0 means they got it wrong. Person number 1 also got item 2 correct, and item 3, and item 4, and item 5. So on average, that person got a score of 1. They got everything correct. Person number 2, by contrast, did not get item 1 correct, but got items 2, 3, 4, 5 correct and got an average of 0.8. Person number 3 got items 1 and 2 incorrect and the remaining items correct for an average score of 0.6, and so on and so forth. You can see person 4 got 3 incorrect, 2 correct, 0.4. Person number 5 got 4 incorrect and 1 correct, or 0.2. So now if you look at the items, you can see that item number 5 is the easiest item in this test because everybody got it right. And item number 4 is second because almost everybody got it right. And item number 1 is the hardest because only one person got it right. That's an important idea, and I'm going to try to flip back. I haven't tried to go back and forth like this, so I'm a little more awkward at this than I normally am. Let me go back for another second to the U article. You'll notice that, let's see, well, they've set this up so that every person has a different uh, number of items correct. But imagine for a second that person number one who got person number two who got item number one incorrectly, and let's pretend for a second that person number five got the first 4 items correct and the 5th item incorrect. So, no, wait, that's not a good example. Hold on a second. Person number 5 got item number 1 incorrect and all the other items correct. So just like person number 2, wait a second, I'm still having, okay, yeah, person number 5 got the first 4 items correct and item number 5 incorrect. Person number 2 got item 1 incorrect and the next 4 items correct. So each person in that case got 80%. They got a 0.8. They got 1 item incorrect and 4 items correctly, but they're different items. So that says something about the ability of the individual items to discriminate between the test takers. And usually when somebody develops a really good test, you want to have some items that everybody passes. Item number 5 would have been the example in that table. And some items that practically nobody gets correct, and that would be item number 1 in the table because only person number 1 got correct. And some items that everybody, that some people get correct and other people get incorrect. So you want to vary the difficulty levels of the items. So the notion here is that you really, in order to really get a sense of how adequately you're measuring a construct, you have to take into consideration the difficulty of the item. And that table that I was just showing you that I'm going to go back to for a second shows that there are a variety of difficulty levels of the items. And so one of the parameters that you're going to see included in modern tests is something about the difficulty of the item. And as I've already mentioned, item number 5 is the easiest. It's got a difficult level of 0.0 or 0, meaning there are no items that fool everybody. And item number 1 has a difficulty level of 0.8. And if you look over here on this average row across here, you'll notice those are the difficulty levels of the item. Item number 1 has a difficulty level of 0.8, meaning 80% of people who take this item get it incorrect. Item number 2 has a difficulty level of 0.6, 60% get it incorrect, and so forth and so on. So the first parameter that we want to be able to take into consideration when we look at a test and how good a job it is doing is what's known as the difficulty level. And I've just shown you a concrete example of that. Secondly, I'm going to go back to this for a second, except we're going to go to another table, also from the U article. And again, I believe this is on the main part along with the syllabus. It's the main part of the Moodle website, so if you want to go take a look at it. Here we've got the example that I was, I guess, trying to come up with in my feeble attempt to do so with the prior table. Here we've got item number 1 and item number 6, both of which have a difficulty level of 0.8. And that is because 80% of the people that take it fail it. And we still have, and that's item number 6 is a new item that's been added here. Item number 5 is incredibly simple because everybody gets it right, and the others vary in their difficulty score. But what's different about this one is that item number 1 and item number 5, which 6 rather, which have the same difficulty level, are not answered the same way by the person that has the highest level of proficiency. And if you look at the averages that are in the final column in this table, you'll notice that the averages range from 83% down to 33%. So that tells you something about the proficiency level of the people taking the test. So here we've got a person who's got the highest proficiency level, meaning they pass 83% of the items, but they fail item number 6. And yet we've got somebody else whose proficiency level is in the toilet, It's only 33%, and the only item they get correctly is item number 1. So we now have a second dimension that we need to measure, which is the proficiency level of the individuals taking the test. Hopefully this is making some sense for you. So those two tables are showing different kinds of things, which is that it's important to look both at the attributes of the item in terms of the difficulty level and the attributes of the examinee in terms of their proficiency level. And so there's a formula that allows us gives us the ability to calculate the probability of answering an item correctly if we know the proficiency level of the examinee. And there's a formula that's in page 109 of your textbook. So as you read the textbook and you read about modern test theory, it'll talk about this particular model, which is also known as the Rasch model. And it allows us to estimate the item difficulty in the context of the person's ability level. And there's a formula there. Please stop me if any of this is not making sense. As the book will tell you, the ability level of the respondent, which you just saw in the previous column in that average, in the previous table in the average column, the ability level of the respondent in the formula is referred to as theta, with the Greek letter theta representing the ability level of the respondent. And the P of theta is the probability for a person that has a particular ability level to pass the exam. You'll also see in the formula, and I didn't put this here on my screen. Let me see if I can find it in the textbook so those of you that have the book in front of you can put these two things together. Hold on just one sec, because I am... Okay, so turning now to page 109, where this first formula is, you will notice that, and this is table 6 or formula 6-1, which if you don't have your book and can't find it fast enough to make this make sense, you might just want to make a note to yourself that the formula that allows us to determine the probability that a person with a defined ability level is able to pass the exam, page 109, is the P of theta, or the probability that the person with that ability level will pass the exam, is equal to 1 over, parenthesis, 1 plus an exponent minus D times theta minus B, and I'll tell you what that refers to. So D is a constant, 1.702, which allows you to convert the item to a normal curve. Exponent is the exponent which is raised to a given power. I'll come back and explain that to you in a second. And B is the item difficulty level. So there are two things in this formula which refer back to the U table I showed you a few minutes ago, which is the theta, which is the person's ability level, and B, the item difficulty. And if you know those two things, you know the ability level of the respondent and the item difficulty level, you can figure out what the probability is that the person with that ability level will pass the exam. And your book gives you multiple examples of how to calculate that. I should point out to you a couple of really important things about the material in the textbook right around this page, and that is that there are some typos. And I've learned this the hard way through teaching this course and trying to make these formula work the way they are written, and there are some incorrect things about that. On the middle site, I have got a little, what do you want to call it, paper in which I talk about some of the typos in the book, and this is one of the pages where there are typos. So what I urge you to do is what I did with my book, is I actually wrote in my book and corrected some of the typos, so you're going to go crazy trying to figure out how to work out these problems. And by the way, when you do the homework, the next homework, please make sure that you include some of these problems, because if you don't, you're not going to learn how to do these problems, and when you get to the midterm, you're going to have an issue. So give yourself the opportunity, even though it's hard and maybe you won't even know how to do it, to try it. See if you can work it out. Get my feedback, because remember, the homeworks aren't graded. You just get a check or no check. If you don't turn it in, you get a no check. If you turn it in, you get a check. And I give you feedback so that you can learn from your mistakes. So give yourself an opportunity to try out these somewhat complicated formulae to make sure that you understand them. So this is really important, and find a way to make a note about this, or you will get some of the problems in the midterm incorrectly. Happens every time because people just ignore this. When you have an exponent which is raised to a negative power, which happens using this formula, every time you have that formula, every time you use the formula, you're going to have it raised to a negative power. And if you don't know how to convert that, you're going to get an incorrect answer. So the note that I have included here as a slide on this PowerPoint is how you would actually calculate that. So I'm telling you how to use your scientific calculator. If you don't have a scientific calculator, most of our computers have a scientific calculator function. And the exponent is, the value of the exponent is always 2.718. So this tells you, first you type in the exponent 2.718, then you enter x to the y button. You can see there's an x to the y button, then the power without the negative, then equals, then the reciprocal button 1 over x, and there's your answer. So it's a little complicated for me just to even read this out loud to you. It makes no sense until you actually have to do it. So make sure when you calculate any of these modern test theory formulae that you know how to raise an exponent to a negative power. And here's how you do it. If you just follow these instructions to the letter, you will get it correctly. And if you don't, you will get it incorrectly. Okay. Yeah.
I have a question about the exponent.
Yes.
So you said it's always 2.718?
Yes.
So as exponent bracket, that means 2, because my calculator can do like modern, I mean, it has like the x and y. So it's like 2.718 to the power of that,
correct.
all that stuff.
Yep.
Is that what it
Yep.
is? Okay.
And the d is always 1.702. So you got minus 1.702 times the ability level of the person minus the difficulty level of the item. So whatever that is, whatever the problem will say to you, what is the probability for somebody with an ability level of 0.5 and an item difficulty level of 0.33, what is the probability that they will pass that item? Okay, and because it's minus 1.702 times the ability level minus the difficulty level, it's always going to be a negative exponent. It's always going to be a negative power, rather.
Okay. So that maybe that's where some of these typos are then.
Yep.
Okay.
Yep. So
I was gonna say,
you'll
makes sense.
You'll find
So I'll
them,
look at
but
it.
if I didn't tell you about this, trust me, you might get it wrong.
Yeah,
And I don't want you to.
Okay, just making
All right.
sure. Got
Okay.
it. Thanks.
Okay, so what we've just described, this particular formula, let me go back up, get another slide. This particular formula, also known as the Rasch model, is, and this is where it's complicated. I mentioned to you that the book talks about 2 different models for measuring, accurately measuring a particular construct. I mentioned a Rasch model, and I mentioned IRT, or item response theory. So where it gets complicated, a Rasch model is what we just described, which looks at one parameter. IRT will be a series of different formula that have 1, 2, and 3 parameters that are being measured. When you have one parameter measured in IRT, you actually have a Rasch model. The Rasch model is measuring one parameter. The Rasch model is one of 3 different formulae within IRT. but it's one that has one parameter. I hope that makes sense for you. The other IRT models increase the number of parameters from 1 in the RASH model to 2 or even 3 models, and we'll go over those in a second. So essentially, when you have the RASH model, it's basically either holding the second and third parameters constant, or it's ignoring them entirely. So I've already said the RASH model looks at the difficulty level of the item or the B parameter, and in addition, in the other two IRT formula, there are the A and C or G parameters. So let's go over what those are. The A parameter is also known as the discrimination parameter, and it tells us how effective the item is at discriminating between highly proficient and less proficient responders. And the C or G parameter is called the guessing parameter. It tells us how likely the responder is to get the correct answer by guessing. So as you can imagine, the IRT models, one of them will include the A parameter in addition to the B parameter, the difficulty level. And the second one will involve both the A parameter in addition to the difficulty level and the C or G parameter. So the second model, the model of IRT that looks at two parameters, looks at the difficulty level of the item and how good the item is at discriminating between proficient and less proficient responders. Notice that in each case, the proficiency level of the responder is always going to be in the formula. The second, or in this case really the third model, looks at three parameters simultaneously. It's going to look at the difficulty level of the item, or the B level, the A parameter, or the ability of the item to discriminate between proficient and not so proficient folks, and the C or G parameter, which is the guessing parameter, which is how likely the person can get the correct response by guessing. I hope this is making sense. Let me know if it's not. So a two-parameter model, this is just saying what I've just summarized for you, looks at two parameters, the difficulty level of the item and its ability to discriminate, or B and A. A three-parameter model uses B, A, and C, which is the difficulty level of the item, its ability to discriminate, and how likely the person is to get the item correctly when they guess. So, and then the RASH model is a one-parameter model. It only has the difficulty level of the item. And all three of these models also include the proficiency level of the individual, their ability level, or theta. So the next point on this slide has to do with a situation where you're the one who's developing the test. And in developing the test, you want to actually go through a process to see how well the IRT models allow you to estimate the person's ability to do well on the test. And if you were going to do that, in order to be able to compute this, you need to have more participants the more parameters you use. So if you're using a one-parameter model, you'd need to have fewer participants in your study to show that the difficulty level is a good way to discriminate. If you wanted to use a two-parameter model, including both the difficulty level and the discrimination ability of the items, you'd need more people. And if you wanted to use a three-parameter model, then it looks at both the difficulty level, the discrimination level, and how guessing affects the score of the person, you need to have even more people. So on a very practical level, you might well understand why in certain tests that are available in print, you would only have a one-parameter model or a RASH model, and that's because getting participants to come into your laboratory to do whatever it is you want them to do, including allow you to develop these models on multiple parameters, to get more of them will cost you more money, it will take you more time, and so therefore you will find that some test developers cut corners and they will only provide you with a one-parameter model or a RASH model. Okay, hopefully you're still
I have a
following.
question. So just to have an idea, what would be a reasonable sample size for running say, a two parameter model? What is the sample size that we would need roughly?
That's actually a very good question. And I'm not sure that I have that answer at my fingertips because I've actually not been in that situation where I've developed a test recently. Back in the days when I was developing tests, we'd never even heard of any of these models. So I don't off the top. What I will do, however, is I will put that down as a question to myself, and I will find out and let you know.
Okay, thank you.
Let me write it down, though. Just give me a sec. How many participants for a 3 parameter? Okay. Okay. I will get that to you. Okay, so the next thing I want to talk about very quickly, because I'm not going to ask you to calculate any of these things, is the book will show you a number of different curves. And I am not exactly sure what pages they start this, but fairly about halfway through the chapter. And these curves, item characteristic curves, or ICCs, describe the relationship between the probabilities that you get and the different thetas, or the proficiency level of the responder. And if the test is easy, it would show you how to estimate the ability level so that it is not higher than adequate estimation. And so we want to make sure that we are able to do that in such a way that we don't get incorrect answers. So the reason I'm going through this, and the reason your book includes these modern test theories, is back in the olden days when I first studied this, all we really knew about was classical test theory. And so we really didn't even have to worry about this. But nowadays, stats have gotten more sophisticated. There are various and sundry programs that allow you to do most of these calculations on the programs. Oh, incidentally, you're going to have to do them by hand, so that's why it's a little more complicated. It's just arithmetic, really, but it takes a little more time than if you had software doing this for you. But there is software available. So the whole field of test development has gotten much more complicated, but there are still people that develop tests according to the classical model only, and there are others that develop it using item response theory or Rasch modeling. So that's why we have to go through, well, what are the advantages of one model over the other? So I think, and I hope that you got this from the U example that I started out with, is that one of the advantages of IRT is that the difficulty of the items are independent of who answers the items, and the person's ability level of the person is independent of what items are answered. So if you used a classical approach to this, an easy test would make people look smart, and a hard test would make people look stupid. And a test that makes people look smart would have a negative skew. A negative skew would mean that there would be more people. If you imagine a distribution, you would have a skewed distribution. You'd have more people whose scores were on the high end of the distribution, and very few people on the end of the distribution where the low scores are, and that would be the tail. So the tail of the distribution, in the case of a test that makes people look smarter, would be negatively skewed because the tail would be pointing to the negative end of the distribution. You might remember this from geometry, that the negative end of the distribution is, if you imagine an axis, X and Y axis, which intersect, and you've got 4 quadrants, the negative end of the distribution is below 0. And where the two axes intersect in a cross, that's the 0 point. And everything to the left of that on the x-axis is in the negative direction. So if you were going to graph it, you'd graph it -1, -2, -3, -4. So a negative skew shows the tail of that distribution pointing to those negative scores to the left of the 0 point. And a positive skew, which is a hard test which makes people look stupid, would look like it would be a situation where the tail, where very few people are scoring in the high scores, the tail would be way down low and it would be pointing in the positive direction, whereas where most of the people were scoring, which is low scores, because it's a very hard test and it makes them look stupid, most of those people will be on the lower end of the distribution. You know, I wish now that I had made a slide to make that make more sense, and I hope that that makes some sense to you in talking about negative and positive skews, because you will definitely need to know this if you haven't already studied that in your intro stats class, what a positive skew looks like on a distribution of scores and what a negative skew looks like on a distribution of scores. So a negative skew, again, the tail is pointing in the negative direction. A positive skew, the tail is pointing in the positive direction. And a positive skew means more people are scoring low. A negative skew means more people are scoring high. So you can well understand why you'd want to be able to graph the scores so that the difficulty level of the test didn't either underrepresent how smart people were or overrepresent how smart people were. So that's one of the advantages of IRT. Yeah.
Michelle, sorry, I have a question on the skewness. Sometimes I get confused whether a distribution is positive or negative. Say, for example, negative skewed. Say, for example, the main pile of scores are on the negative side, but there are very extreme scores on the positive, so that the tail goes towards the positive side because of those very extreme positive outliers. However, the main piles of the main pile of scores are on the negative.
Right, and it's always where the tail is that tells you whether it's a negative or a positive skew. So in the example you just gave, most people are scoring low on the negative end of things. A very few people, a few outliers, are scoring high. So you have a tail that drags off in the positive direction. That's a positive skew.
Okay, great.
Okay, so it's always where the tail is that tells you what the skew is.
Okay, regardless of where the majority of
Right.
the scores.
It's usually the opposite. Where the majority of the scores is usually in the opposite direction. And it's very confusing because, you know, you'd want to say, well, everybody's scoring low, so that's negative skew. No, wrong. That's a positive skew.
Okay.
The skew means where the tail is.
Great. Okay.
So use that as your mnemonic device. Where's the tail? Is it in the positive direction or the negative direction? That tells you your skew.
Right. Okay.
Okay, so let me go back to other advantages of the IRT. So we get a theta, which is an estimation of the person's ability level. And when we graph the thetas, and again, this is assuming we have a whole lot of people. When we graph people's ability levels, we get an almost normal distribution. And you have to, you know, you sort of have to take that on faith, you know, assuming that whatever ability it is that we're measuring, if we have an infinite number of people or a very, very, very large sample, and we were going to graph their theta levels, it would come out as a normal distribution. Because, you know, and this is the principle behind grading on the curve. You know, if you have a teacher that's grading you on the curve, that teacher is assuming that we have scores on the test that are normally distributed. Some people do really, really well. Some people do really, really poorly. The majority of people do somewhere in the middle. When I was in graduate school, I once had a statistics professor that graded us on the curve. So we got a few people that got A's in the course and a few people that got F's in the course. Somewhat larger number of people got B's in the course, and approximately equal number of people got D's in the course, and most of the people got C's in the course. Now, what's wrong with that picture? Well, two things. If you've got graduate students, you probably don't have abilities in the normal distribution. You've got the top 2% of ability levels most likely represented. And to then try to develop a normal distribution based on that is just absolutely incorrect. Of course, the other big problem is in graduate school, if you get a C, that's a failing grade. So by that indicator, if you're giving majority of the students C's, D's, and F's, you're going to weed out your graduate school class pretty quickly. And by the way, that's what happened in my graduate school class. True story, but clearly based on an incorrect understanding of how people's ability levels in graduate school distribute. They are not normally distributed. But in general, in the general population, the assumption is those ability levels are in fact normally distributed. So now in contrast, what would be the advantage So what are some of the advantages, as a summary, of modern test theory? So first of all, you can test whether the items fit a particular models. And you can test the items to see whether they advantage or disadvantage certain groups. Now, you all have heard a lot about discrimination in testing. I'm assuming you've heard that there are some tests that discriminate against certain ethnic groups, for example, or certain gender groups. Well, with IRT, you can test that out and find out whether, in fact, the items on the test discriminate people not on the basis of ability, but on the basis of ethnicity or gender. One of the other advantages of IRT is you can add new items to a test, and you can find out whether by adding those new items to the test, we are continuing to be able to discriminate between highly proficient individuals and not so proficient individuals. We can develop a test and administer it in different languages. And we can see whether by translating the items into a different language, we still have a test that has the same item difficulty level. And it's still able to differentiate between people that have high abilities and those that don't. You can add or delete items that have certain characteristics. We can also see whether somebody has some kind of a really weird response style. Maybe because they're faking or lying or flaking, we can determine whether that particular response style has nothing to do with their ability level, has nothing to do with the item level, but is some other idiosyncratic thing, like maybe lying or faking on the test. So there's some real advantages to a test that is developed using this approach, modern test theory approach, as compared to the more classical approach. With the classically developed test, we cannot add or subtract items, and we cannot do some of the things that are listed here. On the other hand, there are some limitations to the modern test theory. The first one we've already mentioned, and that's the one that I'm going to go research some more to give you some numbers to go with it, which is that we need a much larger sample size to apply it. There are some computer programs that will allow you to do the computations, but they're not very user-friendly, and they're also very expensive. So that means that people like yourself, if you're going to use classical test theory modern test theory, and you're certainly going to have to do that for your homework, is you're going to have to do the computation by hand, and it gets a little tedious. And it also doesn't allow us to figure out whether the items as a unit, that is the total score, how that functions rather than the individual items. So modern test theory is really great if you want to look at the characteristics of the individual items, not so great if you're trying to measure the construct as a whole. So questions now about this material. It's a little dense, but I wanted to make sure that you had some exposure to it other than what's in the chapter, so you understand why we're going through all of these steps in determining the functioning of a particular test using either a 1, 2, or 3 parameter model. So we got a couple minutes. I want to make sure that I can answer some of the bigger questions. If we're not able to get all of your questions in, then we can certainly do this by email. So questions, folks.
So, Misha, I have a question on the very last slide about the
Sure.
sanctions, about the restrictions.
Let me go back to it.
So,
Yeah.
so the last point, where it says that the item response theory does not allow us to ascertain how the items as a unit. So the test, I suppose, has the test as a unit function rather than individual. How about the test information function as well as the item characteristic function? Would a test information function override this limitation, do you think, or is it still very limited in terms of how item response theory assess the test as a whole?
Well, I'm not exactly sure what you're asking me, but I'm going to try to answer it, and if I'm way off in how I'm answering it, I'm going to answer you with an example as to how this might be used. So let's say that you have graduated from fielding. You have the hours necessary to take the EPPP, the licensing exam. And so you take the licensing exam. Now, the developers of the EPPP, the, what's it called? ASPPB, the Association of State Provincial, I forget what the rest stands for, but they're the group that develops the EPPP. What they will typically do is once they give the test, they will use item response theory to determine which items ought to be thrown out. In other words, if there are items that everybody passes or items that everybody fails, they may throw some of those items out in determining what the passing score should be. So even though they're not looking at the total score per se, by looking at the characteristics of the individual items, they're able to determine what a passing score is. So it's not quite what you're asking me, Alex, but it's, I think, fairly close.
No, it makes sense. It makes sense. It makes sense. I was just wondering if, as well as an item characteristic curve, we could item response theory also provides a sort of an average of those items, like a test function, so that we can see how the test as a whole performs rather than the single
Well,
item.
in a way, kind of we do by looking at the probability of the person with a particular theta passing the test. So, you know, and that's what we calculate with each one of these IRT models, is we're really calculating what's the probability that somebody with a high proficiency is passing this test. And if the probability of somebody with a particular, let's say a high proficiency, isn't passing the test, then that would suggest that maybe we want to look at the individual items and throw some of them out and keep some of the others. So that's how I would use it anyway.
Okay, great.
Okay. I know one person has already got to leave because she had another go to meeting. Who else has a question, a quick question, because we're kind of out of time, and I'd like to honor your your time as well as my own, of course. After we disconnect, as I mentioned, I'm going to try to convert this so that it can be posted into YouTube. It'll show you both my screen as well as, you know, hopefully you'll be able to hear me and hear your questions. But if you have other questions, please email them to me. And if they're general enough questions that everybody should hear them, I will make sure that everybody gets a copy of the question and my responses. So, and I will also do the two things which I have committed to do, is to find out something about what kinds of numbers we're talking about for computing each of the three IRT parameter models, and I will also post the answers to homework number 2. I'm not sure how quickly I will do all of those things, but I will do them as soon as I can. So I'm going to say that I'm not hearing from anybody, so I'm going to say good night to all of you, and I hope you have a great evening, and I will get this stuff out to you as soon as I can.
Thank you.
Okay, you're welcome.
Good night.
Bye-bye,
Thank you.
everybody.